in the last talk of the day. I should remind you that the voting for the best talk closes at 5 o'clock today. So decide your best talks and vote for them if you want to have them tomorrow repeated. We're going to have Nikunj Dadhania here. Nikunj works for a Linux Technology Center at IBM, especially on virtualization. In his past, Nikunj has spent a lot of time working on embedded system software with Motorola. So we're having a talk on gang scheduling in Linux kernel scheduler. Thank you.
Okay, it's fine. Yeah. Okay. Hello, everyone.
Hello.
Yep. So today I'm going to talk about gang scheduling. So I have a co-author, is Srivatsa, has not been able to come here. So myself and Vatsa had done this the work and the presentation. So here is the agenda for today's talk. Wherein we'll be talking about a brief intro about what is scheduling, and then take a look at what is gang scheduling. Then a detailed look at what are the kind of use cases that can benefit with the help of gang scheduling. Then we'll dive into the design of the approach, and finally some benchmark results I would be showing them. So next, what is the job of a scheduler in simple terms? So it's an operating system component that decides which task to select and run. So on the charts, what we see here is a processing element, CPU 0, and a timeline of T0, T1, T2, 3, Tn. So the scheduler basically picks a task and then assigns it to the shared processing element, CPU 0, and it happens one by one. A lot of other things that scheduler does, but I just wanted to give a brief here. So adding more CPUs basically gives us a lot of more processing power, but it also adds a lot of complexity. So here we see that there are different colored boxes. So we represent, the color basically represents they are related tasks. They are placed on different CPUs depending on the load, depending on the condition, depending the load balancer would place them at different CPUs. So one thing here, what we note here is the scheduler here does not take into consideration the relation between the tasks. Like suppose there are vCPUs of the same VM. So it can happen that all the vCPUs could be placed on one single physical CPU, or the picking of the tasks can be on the different CPUs would be random on different CPUs. Yeah. So what is it that the gang scheduler would bring a difference to this scene? So gang scheduling is a method to schedule a group of related or interdependent tasks on different CPUs simultaneously. So the similar kind of setup, what happens here is we bring this kind of order, wherein at time T0 we have all the system tasks which would be given the access to CPUs. At time T1 the tasks of group A would be given access to the CPU. T2 it is group B and C. So why is this required? The next question is, so what are the use cases that gang scheduling would help? So I'll touch upon a few use cases here. So one of them is HPC workloads and virtualization. Virtualization in particular, there is a problem called lock holder preemption, which I'll get into detail on Intel, and KVM on power. So HPC. So HPC has been traditionally using gang scheduling from a long time, wherein like it is used to improve the job performance of cooperative tasks. There are commercially available machines like CM5 and Storm. I have some references which actually talk about a lot here. So I'll be mostly talking about virtualization here. I won't go deeper into HPC. So lock holder preemption. So what is this problem here? So here on the chart, what we see here is like I have like 3 VMs running on this, VM A, B, and C. The scheduler would put the virtual CPUs. Each VM has 4 vCPUs, so they are basically placed randomly on different CPUs. So I would like to see at T0, we have the vCPU 0 of VM A. So it's taking some spin lock within the guest kernel and then releasing it. So the green area basically implies a critical section. So and the up and the down arrow is the lock taken and the lock released respectively. So what happens here is basically VM A0 had taken a lock and it was within its critical section. The scheduler decides to preempt it without knowing the fact that the vCPU, it's basically a thread for the scheduler. It doesn't know that the guest kernel might have taken a lock inside the guest. So it basically preempts with the spin lock held. After that, all the vCPUs which would like to take the same lock, like VM A1 and A2, would basically spin all the while, unaware of the fact that the scheduler has taken off, has preempted basically the virtual CPU V1 of A. It is like it is only when T2 where the spin lock is released, the other VMs could, other vCPUs of the same VM could take that lock. But being on the same CPU, the vCPU A0 and A1 being on the same physical CPU doesn't get a chance until he gets a new slice and takes a lock and releases it. So this red colored boxes here are basically showing the busy waiting. So how much this busy waiting would hurt? So I got some numbers here, wherein like on one VM I run a single Kernbench instance. The first row represents that, and the time that is spent on waiting for a lock is less than 0.2%. In the second experiment, what we do is I have 2 VMs, a Kernbench VM and a VM which runs CPU hog. The lock wait time has gone up almost to 7.7%. So basically this time is all spent just doing the busy wait between the virtual CPUs. It's quite a huge number. So there are solutions to this problem. So I would be talking about different solutions that are at present there. So one of them is pause loop exit. So pause loop exit is a processor control feature that can detect loops. This is something like spin locks, busy waits in the guest kernel, and it can cause a VM exit. This is basically done in the hardware. So there are some registers that can be programmed for what is the threshold you want to do the exit, that kind of thing. One of the limitations that it brings in is the guest kernel should use pause instructions in the busy loops or spin locks. It also depends on like tuning the PLE gap PLE gap and PLE window. These are the two tunables required to be tuned to say when exactly to do a pause loop exit after say 1,000 cycles of looping. Do a PLE exit. It also, after doing a PLE exit, the virtual, the hypervisor needs to know who is the lock holder. And on top of that, it requires a new hardware. This feature is available on some of the new Intel processors, Nehalem EX onwards. The next one is parawatt spin locks. So in this case, the spin lock is patched in the guest, wherein it knows that it is running inside the guest. So similar kind of mechanism wherein like it does not spin all the while. It basically spins for some threshold amount of time, and then it does a VM exit. So this is all hoping that the lock holder would get a chance to run and release a lock. What it requires is the guests to be modified. The guest kernel has to be modified for this. Again, the same limitation is the hypervisor again needs to know whom to yield to, and the tuning of the threshold parameter can be tricky. Paravirtualizing spin lock would solve one of the spin lock problem. So what happens to the other busy locks that are there in the kernel apart from the spin lock? We got some of them while we were doing some benchmarking, which I'll be talking later on. So the next use case is Power KVM. So Power KVM has an interesting restriction in a hardware, wherein what we see, what happens is the Power hardware, we can run one partition at a time. So the host OS is a partition, a VM is a partition. So we cannot mix the host threads with the VM threads. Similarly, we cannot mix different VM threads together. So something like this, wherein like if I have like 4 CPUs in a core, so I can have system tasks, and the other CPUs can run other system tasks, or it can be idled. This is not a valid configuration, wherein like you have different vCPU threads of 2 different VM. Even like VM with a host thread is not fine. We can have all the vCPU threads of the same VM, or all the threads of the host kernel, or you can idle it, it's fine, but it should not basically execute different contexts. So this again has been addressed in Power KVM in a tricky way. I'll just go through that. So Power KVM Solution, basically what it does is it has only one thread active at one point of time in the host mode, basically. So what you see in T0, only CPU 0 is active and rest of them are sleeping or basically idling. So whenever it's like it's just about to if I'm scheduling a vCPU thread and it's entering the guest mode, just before that the other cores are brought online and they are scheduled with the vCPU threads, and they also need to enter at the same time and exit at the same time. So the same thing would happen when an exit happens. So whenever they're exiting, we need to make sure that the other threads are offline and only one thread is working. So what happens here is so during the guest mode, we are able to exploit all the CPU threads of the core. But when we look at the host mode, we are only exploiting only one thread. So with gang scheduling, we will allow us to exploit all the threads in the core in host mode. So with this as a background of use cases, like I'll dive into some design aspects of gang scheduling. So as we can see from the previous slides, the gang scheduling problem can be broken into 2 parts. One is the placement, the second is simultaneous scheduling. So placement is basically we need to make sure that the vCPU threads are spread across the core. In the sense, if I have 4 CPU in a core and a 4 vCPU VM, each vCPU has to be assigned to each CPU. This has been achieved using pinning in the current experiments, and simultaneous scheduling is what I have discussed earlier. So let us have some intro about CFS before I enter into how actually we do a gang scheduling. So CFS, as the name suggests, completely fair scheduler, would basically try to be fair all the time. So if I have, say, 4 tasks at the same priority and on a single CPU, the scheduler would try to give 25% of the time to each one of them. So how is this achieved? So it is achieved by something called virtual runtime. So if I have 1 second worth of time, then each tasks should have ideally run 250 milliseconds. So that's what it will try to perfect, and this is done by using a time-ordered arbitrary that we see on the slide, which is keyed on the vRuntime. So all the time, the leftmost node is the best node to be picked. That's the node which needs the CPU the most. There are some scheduler hooks provided basically, so which is known as set next buddy. So if you want to alter the order for some reason, wherein we want to, if a task is waking and it needs to say that I want this task to run rather than the leftmost task. So set next buddy is basically used for such kind of optimizations. So basically the order would be the next, it will see if the next buddy is set and it doesn't break the fairness, then the next buddy is selected. Otherwise, the default case is always to pick up the leftmost task to schedule onto the CPU. So this would run on all CPUs independently. So So what are the changes that we are proposing for gang scheduling? So we are adding a hint called gang buddy. So the gang buddy would pick gang tasks unconditionally. The reason here is we need to make sure that all the tasks come simultaneously on all the CPUs because they are running on different CPUs. So the order changes here, something like the first thing would be the gang buddy if it is set, the next would be the next buddy with the fairness check, and the default case, if both of them are not set, it is leftmost. This is an algorithm slide, and I would actually jump to the next slide to explain that. So how will this thing work? So taking an example of, say, 4 CPU SMP machine, so we need an initiator or an arbitrator which will actually start and stop gangs. Which will send IPIs basically. So what we call it as a gang leader. So in this case we select CPU 0 as the gang leader. So whenever a task is picked on CPU 0, it checks whether this task has to be gang scheduled. There will be a flag which it checks whether it's set to do a gang scheduling. The next thing is if it does, so it's going to send IPIs to its fellow CPUs, CPU 1, 2, and 3. One thing to note here is this selection of tasks or the vCPU on CPU 0 is not influenced. So it is done by a normal scheduling. We are not using the hint on CPU, the gang leader CPU. So that would take care of the fairness aspect here. So the CPUs, when receiving an IPI, would look at what would know that it's a gang task that has to be scheduled, and we'll look into its run queue, that if it has the task belonging to the same gang to be is available on the run queue, it's basically going to influence the scheduler, saying that pick this next, and basically do a set a gang buddy and do a reschedule. So all this is achieved using the task groups for basically grouping the vCPUs, and it's a single noob to enable or disable gang inside the CPU controller group, that is CPU.gang. So what if you have more number of CPUs? So if we do a gang domain of 4 CPUs, then what we have is 2 different gangs running separate gangs on its own. So gang 0 would basically take care of doing the gang scheduling on its own domain, while gang 1 will do it on the other domain. So we can do gang on 8 CPUs, 16 CPUs, but it would whether it would scale up, that's the thing we have to answer. Yeah. Moving on to what are the factors that will benefit gang scheduling. So what we saw earlier was lock acquisition time, where we saw the Kernbench spending a lot of time doing lock acquisitions. Next thing is pinning. So many a times, because of pinning, we'll have a lot of hot cache, and we can get good benefits. The other one is pause loop exits. So lesser number of pause loop exits. The reason here is because all the vCPUs are running, we would the condition of pause loop exit would not be so much. And what are the factors that would hurt gang scheduling? So one is increased idle time, because what if you don't have a task on a CPU to be scheduled? So do you idle the CPU? Or what if a vCPU sleeps earlier than its slice? The next one is increased context switches. So in the relaxed gang scheduling, I'll talk about these 2 types of gang scheduling in the next slides. So and pinning sometimes basically would introduce more idle cycles. The reason being the vCPU task cannot migrate. That is one of the, because we pin them onto a CPU, they are not able to migrate even if the load on the other CPU is lesser. So looking at the advantages we see here is there is no guest modification required. The guest kernel does not need to be modified to solve problems like LHP. It's one of the natural ways to solve the cooperative tasks when you have producer consumer kind of scenario. So it is more natural to gang them up and schedule them together. So as I said, the challenges here is one is fragmentation, wherein what if the examples that I took were all 4 vCPU VMs with 4 CPU SMP. But what if I have numbers of 2 vCPU, 4 vCPU, 8 vCPUs? Then what happens? Scalability that I touched upon, and whether the vCPUs sleep or block early. So depending on how we do ganging with respect to sleeping early, it's divided into 2 parts. It's divided into 2 types basically. One is strict gang scheduling. So here what we see here on the slide is at T0 we have all system tasks. At T1 what happens on CPU 2, there is the vCPU thread A2 is not is sleeping on something. It's not able to run. So one option is to idle it. So in strict gang scheduling we idle that CPU. Similarly, on T2, what we see is B1 runs for a while, and it's done its work. It submits an I/O and it is done. So after that, we idle it. Similarly, like C0 and C1, they are like only two vCPU VMs. So other CPUs are free. So, but still that's idle. So this is a strict gang scheduling. In next case, where we have a relaxed gang scheduling, we allow other tasks to come in and use these CPU cycles, just to make sure that we do not increase idle time. So what happens here is at T1 CPU 2, we allow one system task to come in and use the CPU. Similarly, it fills in. So basically, we do not waste the CPU cycles. So moving on to some benchmark numbers, basically. So this is the benchmark. I'll just go into detail of what kind of setup we had. Is like we had like 8 physical CPUs with HT disabled. Our VM was like 1 GB RAM, 8 vCPUs and 64-bit VMs. We collected numbers for 3 different configurations. One was baseline, then baseline plus the vCPUs are pinned, and gang scheduling with the new scheduler hint. The baseline plus pinned is basically collected to see what are the implications of pinning with respect to gang scheduling. So for each of these numbers, we collected, we ran for 2 VMs, 4 VMs and 8 VMs. So what we would do is we'll start 2 VMs parallelly and run the same benchmarks on both of them. Similarly, 4 VMs, we would start 4 VMs and run in each VM the same benchmark. So basically the overcommitment ratio is 1:2, 1:4 and 1:8. So for per physical CPU, in the first case we have 2 vCPUs. In the second case, we would have per physical CPU we'll have 4 vCPUs, and the last case 8 vCPUs from different VMs. So the first slide here we have is with the PLE. So this is a hardware which has a pause loop exit, the latest hardware, and it has a software which would detect a pause loop exit and would try to give it to one of the vCPUs because it does not know which vCPU holds a lock. So first column here is the benchmark. The second one is the number of VMs, 248, 248. It keeps on repeating. And the third column is what is interesting to us. The fourth column is where we compare the gang versus base plus pinning. Pinning by nature would bring in sometimes will bring in the performance degradation. So what we see here in the third column is we see very good gains on Ebizzy and considerably good gains on Hackbench. Dbench is something which we see worst case performance around like 8%. Basically we go down. So the worst case for this is -8%, while we see the best case is around 68% in Ebizzy. Going on to the non-PLE hardware, you can look at the Ebizzy numbers. So we can see around 330 or 360 kind of performance gains. Similarly, like Hackbench does pretty well. One of the cause of concern here is the Dbench, where Dbench is more of an I/O. It's not much of a CPU workload. So maybe because of that nature, we see that, and we have to analyze that. We tried doing some perf numbers, but it does not reveal a lot of things. I would basically take up a couple of benchmark analysis that we did to show a few things. So for Ebizzy, so what if we basically got some performance numbers from within the VM. So what we saw was in case of baseline, there's a function called flush TLB others IPI. So what happens because they are run separately, a lot of remote TLB flushes that are happening. Sorry. While doing remote TLB flushes, the vCPU would be sending IPIs to all the other CPUs and busy wait on all of them to come back. The next one, what we saw was when we did the when we looked at PLE numbers, wherein like how many times we actually did the exit. So we found that 86% of the time we were actually exiting from this same function call. But the numbers that we got was around 68%. We still got 68% of gain, even with pause loop exit being there. So Gang basically helped to get rid of this busy waiting. Next one is Hackbench. So with Hackbench, the numbers from the performance counters almost looked same. So lock acquire, if you see both of them, they were like plus or minus 1, which does not give us much clue about what is the reason for the gain, because if you look at the table below, we are saying that we saw around 18% of gain in the number, but the performance counters didn't give much detail. So getting more deeper into the locking statistics, which actually tells me that how much time was spent on the lock and how much time was spent to acquire the lock acquisition time. So we had to get into a debug kernel to get this. So I had put the reference for debug kernel. So when we put on the debug kernel, the number has gone pretty pretty high, and the difference has gone down. But the thing to note here is the lock wait time again. So what we see here is between the baseline and the Gang, we see around 60% of gain with respect to the Gang scheduling. So we gained this much amount of time not waiting for the lock. And because of that, we could explain that we had the gain in the case which we didn't have debug enabled. So okay. This was a small experiment that which we initially tried to get in before doing the benchmark. So to see whether if we do Gang scheduling, will we really get some good numbers? So this was an interesting setup wherein on a 64 CPU machine, what we did was, and it was pause loop enabled. So we'll have two instances of the generation growth program. So we wrote one program wherein like we would increment. So if I have a 64 CPU machine, then I have 64 threads in that program. So each threads would basically increment one global atomic variable once in a generation. So what is a generation? So generation is basically 0 to 63 is the first generation, then 64 to 127 is the next generation. So each thread would get once to increment during one generation. And we run the two instances of the same program on the machine. The ordering here is not really important. Which CPU comes and increments it, that's not important here. And we would basically do a count till million. So if you see the Gang number and the baseline number, so we see around 66% of gain with respect to the real time. So it might be more if we calculate the total time, but with respect to real time, we gain around 66%. So the current status is we have the patches put on to LKML and some discussions, nice discussions we had and some flames. So and the future work would be, the first one is basically we need to compare the gang scheduling numbers with, there is some work which is going on with paravirtualizing spin locks on KVM, which is still in the works. So compare the numbers with that. The next one would be like strict gang scheduling for power KVM and HPC. So HPC is the one thing which we want to go ahead and see what difference the gang scheduling will make there. Next is acknowledgement. So Parata and Vatsa had been helping me on this a lot last year. So thanks them a lot. Some references. So, yeah, legal stuff. And Q&A.
So which one was first?
I might have misunderstood a lot of this stuff, but what if you had CPUs with odd numbers of cores, like 5 cores? Because some CPUs, like the NVIDIA Kernel, it has 4 main cores, but then a 5th companion core, which is meant for like tasks. Would this cope with that, and would you just have the 5th core being the gang leader? Or
you can actually do that. It's like we can have like 5 core. You define the gang domain size as 5 CPUs.
Okay, I wasn't sure if it was that flexible.
Yeah. It's possible. But then vCPUs have to be like 5 vCPUs, VM or something like that, or basically to not have fragmentation or that kind of issue.
Yeah, makes sense.
Yeah.
And also, I thought you couldn't do relaxed gang scheduling on power.
Yes, you cannot do relaxed gang scheduling on power.
It's just because in the slide before it said the to-do was to do strict gangs.
Right. Okay. So relaxed gang scheduling would something?
Oh, you can.
Yeah.
No, it's all right.
So relaxed gang scheduling would basically not work on power because of the hardware limitation that I talked about.
That's not quite true. I mean, you can do relaxed gang scheduling. You can't combine it with the guest.
Yeah, same thing. Yeah.
Yeah, because of the context.
Right. Right.
Isn't the nature of relaxed gang scheduling that it uses multiple contexts? Or I probably misunderstood.
Right. So I'll touch that again. So the power has a concept of partitions. So the host OS is one partition, and it has one context. So when a new guest comes, that's a new context. Okay. So all the guests are these are partitions, and they have their own contexts. So because of that, you can't mix the threads from different contexts together.
Okay.
Yeah.
There was a question here, remember.
How much noise is there in those benchmark results? If you rerun the benchmarks, how much do they vary? Because some of the curves look a little bit odd, and it's hard to tell if that's telling you something real about hot points in the number of tasks or whether it's just noise.
Some of them, some of the benchmarks I have seen are noisy, but Ebizzy and all, they are pretty consistent. Yeah, Ebizzy and Ebizzy is consistent. Kernel is consistent. Yeah, SpecJBaby is one of the thing which we saw a lot of noise, which is sometimes pretty weird. Sometimes, yeah.
You still have like 7 minutes if there's something to add.
That's it, I guess, yeah, for me. Yep.
Okay, so
Thank you,
there's no more question.
Yep.
We're going to end up day 4 of the conference. Thank you, everyone. I hope you vote for your good talks, and we'll meet you tomorrow for the last day. And I want to thank you too. I've included 2 thank you cards, one for the other author. Say thank you on behalf of the LCA team this year.
Sure. Yep. Thanks a lot. Thanks.